Okay, welcome everyone to today's Autonomy Talk. Today we have with us Dr. Ivan Ruchkin, who is an assistant professor at the Department of Electrical and Computer Engineering of the University of Florida, where he leads the Trustworthy Engineered Autonomy Lab. His research makes autonomous systems safer and more trustworthy by combining techniques from formal methods and artificial intelligence. Ivan received his PhD degree in software engineering from CMU and completed his postdoctoral training at the University of Pennsylvania. His contributions were recognized with multiple Best Paper Awards, and we're very happy to hear more about the interesting topic from Ivan. Thank you very much, and the stage is yours, Ivan.
Yeah, thanks, Mark. Thanks for having me, and thanks to IROS for making sure the audience is not too packed here. So we have time for questions, discussion, and everything. I'll encourage everyone to ask questions as we go. Otherwise, we may move on and lose track of the interesting topics. All right, so today I'll tell you about the verified and monitor methodology and the calibration guarantees that we're providing on top of it. But first, there'll be a few slides of kind of general introduction. And so I assume most of you have heard of cyber-physical systems, but for those who haven't, it's a broad class of systems that includes robotics and then some more on top, like smart grids and smart cities. I prefer to define CPS as the class of systems that are driven by software operating autonomously in the physical world. And the premise of the whole field is that the same set of techniques can be used to design and engineer and assure these systems. So what do we want from CPS? Well, we want safety. It's a big and unsolved problem right now. We don't want them to do anything harmful to themselves, the environment, or the people around them. But we also want trustworthiness. That's a complementary property that basically says that the CPS should operate the way we expect them to. And this is not the same as safety, because even a perfectly safe system may not be trustworthy, and if nobody trusts it, we're not going to deploy it, and we will not reap the benefits that all these systems bring to our lives. At the same time, the system doesn't need to be perfectly safe to be trustworthy. We just need to know when it works well and when it doesn't work well. And so in pursuit of these two properties, me and a number of other people in the communities are working towards strong and comprehensive guarantees for safety, especially difficult in uncertain situations. And also I work on monitoring and prediction of failures. That's the cases when we cannot have perfect safety, but we still may be able to retain trustworthiness if we know what the system is going to do and when to stop it before it starts, creating a lot of problems for us. So a bit of a plug here for the CPS community. It's a rapidly growing community. You can see the number of mentions of cyber-physical each year on Google Scholar, and it's growing. I took this picture in 2022, but I'm sure it's still growing. I'll need to redo it. And at least in the US, it's well funded at the federal level. I'm sure in Europe, there's also plenty of funding for this kind of work. I started working on CPS more than 10 years ago, and this is not to attribute any growth to me specifically, but I've been part of this community. I really enjoy it, and I invite others to check it out. The CPS week deadline is at the end of the month, at the end of October. So if you have some papers on the topics like I'm discussing today, please feel free to check out the conferences in the Cyber Physical Systems Week. Okay, so with that said, another plug for my lab. So in pursuit of this safe and trustworthy autonomy, I'm leading this T lab at the University of Florida. And we're trying to make CPS better through rigorous engineering and strong guarantees that come on top of that. We try to work across many domains, not particularly focused on any specific one, but some CPS are harder than others. So we're working with driving, with mobile robotics, and flying and underwater drones. As far as techniques, they primarily come from the formal methods and AI machine learning, and get applied to problems in CPS and robotics. And I try to work end-to-end in my research. So I start with theory. We have some theorems that typically give these strong guarantees that we want. Then the theory informs algorithms that form the basis of engineering techniques and tools that can be used to engineer a variety of systems. And then we try it out by deploying the algorithms and the models on the specific systems and simulation and physically. So for physical deployments, we are right now targeting autonomous racing. So many of you have heard of the F-110 community. There's also donkey car community for camera-based cars. So that's our research platform in the lab. And this is me. A couple of words about myself as a matter of introduction. I grew up and did my undergrad in Russia. That was in applied math and computer science. Then I moved to CMU, where I worked on software engineering and formal methods. And finally, I spent a few years as a postdoc at UPenn working on guarantees on learning-enabled systems, which is what I'm continuing to do now. And in between these, I had a chance to have some industry jobs, mostly in the domain of software engineering at different levels. Okay, now that we're done with the introduction, let me go to the meat of this talk, this verified and monitor methodology for cyber-physical systems with machine learning in the loop, which these days is difficult to avoid. So let's say we're trying to build this system here, some self-driving car. So what do we do first? We'll need to collect some data from the environment where this car is going to operate, maybe some pictures or videos of the city streets. And we need to build the models of this car, or for this car, for example, how it moves, how it responds to controller commands, and so on. Then we plug the data and models into the training and synthesis algorithms, which will spit out some components for the car. Primarily, we'll focus on control and perception. Here I draw them as neural networks, which is increasingly the case, but sometimes it's a more complicated pipeline than just one neural network. And we want to handle all of that. But once we make such components, they go into the system, and we say that we've implemented an autonomous system. Of course, if we want guarantees on top, we'll need to do a bit more work. And we'll need to put the data and models into the verification, which is a different class of algorithms that provides guarantees, for example, that the car won't crash into any pedestrians. And the guarantees hopefully apply to the system, and then we're really happy. But if any of you have tried, marrying the theory and practice, you know that very often the theorem says that the system is safe, but then you deploy it in practice and it's crashing all the time. And so there is this gap between theory and practice, between the guarantees and the real executing autonomous system. And of course, many people are trying to close this gap, but it probably won't be 100% closed anytime soon. So to have some safety and trustworthiness in practice, what people have been doing is deploying monitors. So monitors are these runtime online components that are observing what the system is doing, and they're also looking at the safety guarantees, and they're trying to come up with a verdict of whether the guarantees apply at a given moment right now, or maybe in the short-term future, say in the next 30 seconds. And with these monitors, we kind of get to close this gap at runtime using the most recent observations without trying to reason about all possible situations, rather focusing on the here and now. So that's the verified then monitor methodology. I didn't come up with it, so let me give a few examples of people doing this. So one example from IROS 2020, actually, people at Boulder took hybrid system formalism. So hybrid system here is a combination of differential equations and discrete jumps, applied classic reachability methods, and then Bayesian estimation on top of that for monitoring, and they had some version of this methodology instantiated. Then folks from Europe, from Italy, I think, repeated a similar trick, but replacing reachability with a neural network that predicts reachability, and then conformal inference on top of that. People at Berkeley did the same thing for the stochastic case with Markov decision processes, model checking them, and then again Bayesian estimation at runtime. And finally, in ICRA this year, the folks working on Hamilton-Jacobi reachability at USC have instantiated a similar pipeline with neural network prediction and Bayesian estimation at runtime. And there is more Hamilton-Jacobi papers that follow a similar approach. So this methodology is kind of, I didn't invent it, it just emerges from several recent papers of how to provide these safety assurances to systems in practice. But here's the gap in what the papers have addressed so far. The storyline is basically, well, we want safety, so we do verification. Oops, verification didn't get us far enough, so we're going to make monitors. Well, the remaining question is, will the monitors get us far enough? And the papers provide some empirical results, but not much theory on this question. So let's look into this question. Are the monitors good enough? So I'll define what it means in my context, and then we'll proceed to look at how to figure that out. So let's consider the confidence monitoring context. That is, we have safety. It's a binary random variable. It's either 0, we crashed, or 1, we didn't crash. And you can think of it as some safety in some future horizon, say over the next 30 seconds. And we're given observations. That's all the raw sensory data that your system is observing at runtime, camera images, LiDAR scans, and so on. And so the question that the monitor is facing is, what's the probability of safety given the observations I'm seeing? And the monitor will output some confidence C that will try to approximate this probability. So that's just the confidence setting. It's slightly more flexible and informative than just do binary classification. Will we crash or will we not crash? So in the setting, to ask how good is the monitor, we can use the expected calibration error. It's a recently popular metric, primarily in the machine learning community, for any probabilistic forecaster. Intuitively, it's essentially a mean absolute error between the predicted and actual chances of safety. And I'll show here how it's formalized, just to be precise. So the ECE of confidence C with respect to safety S is the expected value of the absolute difference between the predicted safety confidence and the true probability of safety when we make this prediction. So for example, if in some situation before some turn, our monitor is predicting 80% safety, but then we repeat this turn in reality multiple times and only 70% of them are actually safe, that means we have ECE of 10%. And of course, the ideal ECE would be 0%. That would be called perfect calibration. And so now the perspective shift and kind of the advance that we've been making is that if we want the system to be trustworthy in the absence of absolute safety guarantees from our verification, we will want the monitors to be good. And specifically in this context, good means having an upfront upper bound on the ECE, hopefully small, but some epsilon that we know upfront, then we'll be able to trust our monitor plus minus the epsilon with the safety predictions. On the other hand, if we don't have the epsilon and the monitor can be arbitrarily wrong, then it doesn't really close the gap between safety guarantees and the real system. All right, so that is obtaining this epsilon and setting things up so that it's obtainable at all will be the problem for today. And I'll talk about two contexts in which we're able to do it. One would be the probabilistic context with Markov decision processes that get verified, and then we do Bayesian state estimation. And the second one is the context with hybrid systems and neural network reachability. So it's non-stochastic in the system model, and then all the stochasticity is happening at runtime with assumption monitoring. And once I cover these two contexts, we'll be basically done with today's talk. So next I'll go into the first one, but I want to give people an opportunity to ask any questions or raise any concerns about the overall setting of this methodology and the problem formulation that I just described. All right, let's assume there are no concerns. If there are any, feel free to put them in the chat. So let's talk about this first setting, which is based on the recent NASA formal methods paper. So I'll explain the setting on an example of water tanks. It's a classic cyber-physical system. There's two water tanks, the water is flowing out of them, and then there is a tap that we can use to put water into the tanks. Let's say they're both draining at a constant rate, although the stochastic rate could also be handled with our approach. And we have a noisy sensor of the water level. So this is where, you could be using a neural network. There is some unknown uncertainty in how well the sensor is working. And we have a deterministic controller that somebody already designed for us. It can only fill up the tank, one tank at a time. So the safety here would be keeping the tanks from underflowing and overflowing. Let's say there are some thresholds defined. We don't want them too full or too empty. And let's say the horizon of this assurance is 10 next steps. Let's say 10 seconds or something like that. So let's instantiate this methodology for the water tank example. We have this dynamical system that I just described. We will make an abstraction of it into an automata model. Then we'll verify it and obtain the verification results, which will essentially tell us how safe is each state. And all of this will happen in design time before we deploy it. And then at runtime, we'll obtain state estimates, pass them essentially through this table of verification results, and get the probability of safety in the next so many seconds. So this is a straightforward instantiation of this verified and monitor methodology for this system. And so now, since we have time, I'll go through the details of each step, kind of telling you more about these abstractions and verification results. But if we follow this methodology, here's the guarantee that we'll get in the end. Right now, I'll say it informally and then concretize it later. So if the abstraction is conservative, which I'll tell you what it is, and the state estimator is well-calibrated, which means it's telling us close to the true distribution of the states at runtime, then the safety estimates will be conservatively calibrated, which means we won't overestimate how safe we are with our tanks. So let's go through the details here and then see the formal version of this guarantee. We'll start with a conservative abstraction. So, and this is a more or less standard methodology here. I'll just go into the details for the educational value of it. So we have this original dynamical system, which it has continuous states and may have continuous time. And we want to create a discrete state model that contains all the behaviors of it so we can later verify it. So here's an example of what this abstraction would look like. So this is our state space. X, Y axis are the water tank levels. And let's say we have region 1, from which we're starting. And then we apply our dynamical equations, we end up with region 2. And if we're trying to discretize the state space along these grid lines, the region 2 doesn't fit neatly into the cells that we're trying to make. So this means that our abstraction will say that from region 1, we can reach actually 4 different regions, 3, 4, 5, and 6. And we don't know which one we will reach. We cannot even assign a probability to it because we don't have detailed enough knowledge of how the dynamics works. So that will be the non-determinism that we'll handle in the model later. Basically, there's 4 possible transitions from region 1. That's how we construct the discrete states and transitions. Let's talk about the automaton model. So we'll use probabilistic automata. Those of you not familiar, the main reason why we're using them is that they allow us to handle both probabilistic behavior from the stochastic underlying system, that noisy sensor that I talked about, and the non-determinism from the abstraction. So here's an example automaton. It consists of states, that's the circles, actions in red, and transitions in blue. So the way it works is first, the action needs to be chosen. Suppose you're in state S0. If you chose action A, then with probability 1, you end up in state S1. If you chose action B, that's where you roll the dice, and with 80% chance you're in S2, otherwise you're in S3. And that's how execution always works. First, the action is picked, and then there is the probability flip. So the actions here, even though they're called the actions, are not representing the controller actions. The controller actions we already know. Somebody designed the controller for us, or maybe gave us a neural network that chooses the actions. So the control commands. The actions here are going to represent this uncertainty in the exact behavior of the system that I showed on the previous slide, this discretization uncertainty. And that's why we need the actions. And the blue probabilities are for the original, stochastic aspects of the dynamical system. And so I think some people are working on it from a different perspective, from kind of the stochastic process perspective. And they might say, well, why don't you use our stochastic process? And well, the issue is that for computational reasons, stochastic processes often need to impose assumptions on the noise that they're having, on this noisy sensor. For example, they say it's going to be a Gaussian noise, and then we'll learn the parameters. And that's fine, but the noise is not always Gaussian. And I personally don't feel as confident in handling the non-Gaussian noise by using a Gaussian stochastic process. So I don't know what happens in that case. I don't know how to quantify the errors. Whereas with a probabilistic automata, you can handle any distribution you want, and the inaccuracies of modeling are explicitly represented with these non-deterministic actions, which helps. So that's just the modeling choice that we're pursuing here, and we know how to handle it conservatively, which I'll explain in a moment. So now we need to make the whole system, kind of put the whole system into this probabilistic automaton. So we're given the dynamics, controller, perception, that's the sensing and some neural network, and the state estimator as well. So for the dynamics and control, we'll make this non-deterministic abstraction we talked about. And for the perception state estimation, we don't have a kind of symbolic description of what they're doing, but suppose we have some data set, and we're going to learn a probabilistic model of them and compose it all into the overall system model that we will call MAS. So everything we know is described in the probabilistic automaton. So with that, we're ready to do the model checking or verification of that system. A bit about the safety property first. So we need to formalize it. In the original dynamical system, the property would look like this. In the temporal logic, saying globally up to horizon T, our dynamical state is not going to be an unsafe region, which is water to high or water to low in our example system. Well, we need to translate this into the abstract version of the automaton, which is that the abstract state S prime is not in this abstract unsafe region, which we are abstracting the same way we were doing before. So let's say our unsafe region is an ellipsoid, and we need to discretize it. Well, then just to be conservative and safe, all of the cells where there is any unsafe state are going to be declared unsafe. So we know how to handle such over approximation with this model, which helps us derive the guarantees. Okay, so we know what is safety in our system as well. So then we're ready to verify safety. That's called probabilistic model checking, and there's a number of tools off the shelf that we can use. Essentially, it's an algorithm that computes minimum and or maximum probability of a safety property on a given probabilistic automaton, while accounting for all possible non-deterministic resolutions. That is, all the choices of actions A and B. The reason why there is a maximum and minimum probability is that depending on the choices, you may end up with a safer or less safe system. And since we are interested in verifying system here, we will try to minimize the probability from this model over all possible actions, just to be safe. And if we execute this right, there's a guarantee that our computed probability of safety will be upper bounded by the true probability of safety from our dynamical system. So that's the benefit of this abstraction. We can always find a lower bound for safety and not be overconfident, at least in the verification step. Okay. And by the way, people who do controlled synthesis, they would go the opposite route and try to find the probability, the maximum probability of safety. And the choices of the actions are going to be their control policy. But that's in a different world. We already have a controller. Okay, so What we do with this model checking, we essentially take every state in the system and verify the safety property from that state, computing this probability that I just talked about. And there is a finite number of states since we discretized it, and it's a bounded state space. So in the end of this process, there will be some computation. It's not quick to do this, but eventually we'll end up with this table that says if we start in this state, this is the probability of safety we get. If we start in another state, this is the probability, and so on. And so we essentially know how safe each state is. And that concludes our offline or design time process. Now we go into the runtime with this safety map and try to use it to predict safety in the next so many steps. So here we're going to exploit this total probability formula. So our estimated probability of safety is essentially a sum of two things. One is the chance of the system being in some state, which is going to be obtained through estimated current state. And the second one is the chance of the state being safe. Well, and we know this because we did all the verification. And what we need to do to compute the sum is to essentially pass this distribution through this table to the weighted combination of them. And that gives us the probability estimate. So yeah, this distribution comes from a state estimator, and this methodology works with a variety of them, Kalman filters, particle filters. We did a Bayesian state estimator in this case study because it just made more sense given the observation and state space. Yeah, we basically just compute the sum literally at runtime at every step. And so now that and that's all there is to the online monitoring. Now that we've gone through that, we can instantiate this conservatism guarantee in a bit more precise way. So there's two premises and one conclusion here. One is that the abstract model is conservative. That means that we get the lower bound of the original system safety. So we discussed that this always works if we build the model right. The second premise is that the state estimator is well calibrated. So what this means is that for each estimated state probability being P, the true chance of being in that state is P. So this is perfect calibration of the state estimator. And well, it's a strong assumption. And I actually think that this theory can work even if we weaken this assumption, but for the sake of pushing this theorem out, we have to assume this. Also, there's not many state estimators that officially can give you this guarantee. So if any of you know state estimation well, and estimators that upon convergence can give guarantees along these lines, or maybe up to some epsilon, we should talk. But for the sake of theory, let's assume it's well calibrated. Then we get our conservatism guarantee. What does that mean? That means this, if we predict probability of safety to be P, then the true probability of safety is going to be at least P. And if you look closely at this, you'll realize that this is a one-sided version of that ECE constraint that we've been trying to get. So we will never be overly optimistic. We may end up being pessimistic, and that primarily depends on how pessimistic our model is. So if we build a good model, we'll get probabilities close enough to the true safety. All right. So that's the whole theoretical benefit of doing it the way I showed. Let's return to our water tanks case study and look at the results. So this is a reliability diagram, which is a typical way of showcasing the calibration of probabilistic predictors. X-axis is the predicted chance of safety, y-axis is the true safety, and you can see that they're pretty well aligned. An ideally calibrated predictor is going to be perfectly along this dashed line. So the ECE is low, Breyer score, which is another metric for calibration, is low. So that works pretty well. Calibration alone is not strictly speaking enough to have a perfect classifier. So we need to look at the area under the curve, and we're performing well in this regard too. So our monitor is green here, blue is a baseline, and red is the true true estimator that always knows the true state of the system. And we can see that we get pretty close to the true state performance. This means that we lose very little on the runtime uncertainty. And the true performance is kind of the upper bound for our performance, because, for example, if you're predicting a coin flip, the upper bound is 50%. If the system is stochastically uncertain, you cannot have a perfect classifier here. So this is all to say that on this case study, this methodology worked well. Okay, so this concludes the first technical dive of the talk, and the second one will be shorter and more high level. But if anyone has comments or questions on the first part of the talk, I encourage you to ask them now, because we'll move on from this material to other things.
Hello.
Hi.
Screen. Hello. I just wanted to quickly ask, in the automata stage, how do you identify the probabilities of certain actions occurring?
Yeah, that's a good question. Let me maybe go to this slide. This is the closest I have. So yeah, there's two kinds of actions or transitions that are involved. One is, what will the controller do in a certain situation? Well, that is easy to answer. We don't even need the probability, because for each situation we have the kind of full description of the controller. It may be some, PID-like thing or MPC-like thing, or it can be even a neural network, but it's a deterministic process. You give an input, you get an output. So for any input we care about, we can get an output, and that's that. The probability is needed to figure out if we are in a true state S, what will our perception say our state is, and that estimate is going to go into the controller. So that we don't have anything fancy. We basically say we collect some data, which is pairs of true state and estimated state, and from that data we just construct a distribution over the possible perception things. So that's essentially it's a discrete distribution over all possible estimated discrete states, if that makes sense.
Yeah. Okay, thank you.
Mm-hmm. Thanks. Anyone else wants to ask anything? No, okay. So let's move on. This was the stochastic context with probabilistic model checking and Bayesian state estimation. Let's look at the second context, which has kind of the stochasticity localized to runtime only. And this is based on another paper from Conference of Cyber-Physical Systems in 2022. So I'll explain this example on the case study of the underwater vehicle. So it's essentially an autonomous torpedo that is supposed to follow the underwater pipeline and scan it for cracks. You see the pipeline in blue. It's all sonar based, so it's scanning with a side sonar, and it's also supposed to avoid obstacles like this gray box with a front sonar, which it sometimes fails to do, as you can see in the video, and that will be our safety violation that we're trying to predict. So there's two requirements here. One is not colliding with obstacles. The other one, not losing the pipeline, because then we're kind of lost in the ocean and we don't really know what we're doing there. To accomplish these two tasks, we're measuring the distance to front obstacles and the position with respect to this pipeline. And to accomplish the safety prediction goal, we will also have several confidences. So we'll have the detection confidence, how well we can see the obstacles ahead of us, the confidence in seeing the pipeline on the side, and also the dynamics confidence, that is, that we're sure that the system is controllable and stable, and that it performs the way we expect it to perform. And this may not always be true, for example, if there are some problems with the fins or the thrust. So let's instantiate this verified and monitor methodology for this system now. And this instantiation is called the COCO, the confidence composition framework. Again, there is a design time phase and the runtime phase. At design time, first we need the safety requirement. And since there are two requirements, they need to be married somehow into one binary one. So temporal logic here. Essentially, we're saying that in the next 30 seconds, you have to be tracking the pipe. You have to see it well and be positioned well with respect to it, unless you're avoiding an obstacle. If there's an obstacle ahead of you, feel free to ignore the pipe and just avoid the collision. So that will be our safety requirement. And this, again, over some time window in the future. And let's say we do all the modeling. So here we have a neural network controller that tells the vehicle what to do. It determines the fin positions, allows it to turn and so on. We have some environment model of the pipe, the dynamics model of the vehicle, and the perception model of how well we can see the pipe, an obstacle, and so on. And we will use here the closed loop neural network verification. This is kind of a recent area in assuring these machine learning enabled systems. It's not my work, it's one of our collaborators' tool that we will use for this. So I won't go into too much detail, but I can talk about it if you'd like later. So this is actually difficult to use because it takes this controller and converts it into a dynamical system and just starts verifying the bigger dynamical system. So whenever you try it in practice, you usually don't get anything conclusive from this process. So to get it to work, you need to make some extra assumptions on the model here. So for example, in the environment, you assume that the obstacle is far enough and that you're tracking the pipe right now. That's kind of the initial state of your dynamical system. Then for the dynamics, you assume that, well, you're not perfectly behaving the way the system does, but at least the observations are consistent with what you think the dynamical model is. And then we put some bounds on the perception noise, because if you don't see the obstacles or the pipe well enough, you're not going to be able to avoid collisions or avoid losing the pipe. So then we take these assumptions, and so this is a key step in this work. We need to combine them. And here we combine them with a Boolean logical formula, saying that basically this is a scenario under which we're trying to verify the system. And that adds extra constraints to the verification process, which speeds it up and makes it more successful, less uncertain. And let's say we manage to get the safety verdict from it. So the system is safe, which is great. This is the design time part. The only part remaining is that the assumptions may not be true at runtime. So we will need to monitor them. And I won't go into the details of monitors, but there are techniques to obtain some confidences in all of these assumptions. So let's say we build these, the monitor for each assumption. We deploy it at runtime. At runtime, each monitor is outputting some confidence. That's the number between 0 and 1. And then they're plugged together into a key piece of this framework called confidence composition, which outputs the overall confidence C in the combination of the assumptions and indirectly quantifies the confidence and safety guarantees. And so this is, again, a form of this probabilistic safety predictor that we want to have. So there are many moving pieces here, but many of them are kind of standard techniques, just applied in the right place at the right time. The hardest part is combining the confidences in assumptions to get the overall safety confidence. So I'll take one slide to go through the details of that. So let's clean up the picture. So again, our safety is a Bernoulli random variable, either yes or no, in some time horizon that we already fixed. And we want to calibrate C to S. So we want to take this expected calibration error and impose an upper bound on it. And this is tricky to do because the monitors were kind of developed independently and they may have unknown statistical dependencies. They're also not perfect. Unlike in the previous work, we're not going to assume that the monitors are giving us the exact true probability of the assumption holding. So doing this directly is tricky. So we'll do this indirectly. Remember that each monitor has the underlying assumption that it's trying to tell us about. For that, we can actually calibrate the monitors. We use the standard machine learning techniques to calibrate monitor 1 to assumption 1 and obtain some upper bound based on our data set and so on for each monitor. So that can be done. And then remember that under the combination of assumptions, we have a verification that guarantees safety deterministically because all the whole model is deterministic. So if the assumption is satisfied, we always get safety, period. And so the trick here is, instead of predicting safety directly, we will try to predict the combination of the assumptions using our composed confidences. And we have a theorem that reduces the safety problem to the assumption problem. Essentially, it says that if we can manage to calibrate our confidence to the assumptions with some bound g, which is a known function, then we get the original calibration to safety with this bound. So this allows us to forget about safety for a moment and just focus on calibrating confidences through the combination of assumptions, which is still not easy, because essentially what we're asking here mathematically is what's the probability of a Boolean logical formula being true if we know the individual probabilities of each of the Boolean variables. And we don't have the straight answer to this because we don't have the full joint distribution of these Boolean variables, just the marginal the probabilities of each variable. So to get this solved, we kind of, yeah, right, there is also the logical part, but you can kind of take the formula apart using the standard techniques and the axiom of probability. So this boils down to the conjunctive composition of ECE's problem, which was formulated in this paper. And here's what it looks like. So if you have two monitors and their respective assumptions, and you know the calibration bounds on each, we need to find some function f and the associated constant EF that the ECE of this functional combination of the two monitors is well calibrated to the conjunction of the assumptions with this constant EF. So you can see here the interplay between the continuous probability values of the monitors and the conjunctive underlying assumptions. And this is different from the typical mixture of experts setting where there is multiple probabilistic forecasters trying to predict the same underlying binary truth or non-binary. But in this case, they are predicting different truths and we're trying to combine them with conjunction. Anyway, long story short, we managed to obtain such bounds for a couple of closed form functions. That's product and weighted sum. The bounds don't look nice, and sometimes there are some other variables there, like the variance of monitors, but it is a guarantee. And then we also considered data-driven solutions to this problem, which don't give us the exact bound, but they may perform better in practice, at least in the average case. So we have a variety of ways to solve this problem, which then allows us to compute this probability of an arbitrarily big logical formula, and it satisfies the precondition of this theorem, which ultimately gives us the sufficient condition for calibrated safety. So in this context, we managed to get a two-sided bound on the calibration error of our monitors. All right, so let's look quickly at the experiments here. So we perturbed these assumptions randomly in the simulator and ran this underwater vehicle. Sometimes the assumptions didn't break anything. Sometimes it actually violated the safety. And so in the results, it turned out that the composed confidence is better calibrated to safety than the individual monitors. So it's kind of, you know, the whole is better than the sum of its parts situation, which is what you want in a good compositional method. So here's a quick peek at the data. Let's say we have two monitors for our assumptions, and they have some calibration errors, which are pretty big to safety. But then we compose them and we get the error of the lowest one. And this is without using any extra data. So we can pick the better one, even though we don't know upfront which one was better. And then if we throw some data into the equation, we can reduce the calibration even further to something like 7 or 8%. So you can imagine that if your monitor is telling you you're 80% safe, then you're going to be somewhere between 73 and 87% safe. That's what it gives us. So you can more or less trust your monitor within this interval. That's what this result means. And there is a similar result for the mountain car case study. You can see it in the paper. I won't go through that now in the interest of time. Okay, here I need to acknowledge my collaborators from UPenn and also Rado from RPI, who made that tool for verifying neural networks. Okay, so this concludes the second dive into the hybrid system and assumption monitoring setting. Maybe this is a good time to take a quick break and see if anyone has questions about that setting, and then I just have a couple of slides to conclude. All right, let's move on. So a quick mention of what I'm up to right now. So all these systems that we've been talking about, they have controllers, but they don't go directly from images to control actions. Usually there's a perception step. But many people in robotics, as you well know, just want to do end-to-end, pixel to action control. And it's difficult to provide guarantees for that. So we're working on one project to do that right now, trying to approximate a high-dimensional controller based on images with a bunch of low-dimensional ones, which are easier to verify. Going even further in the kind of pixel to action control, if we have a system with a not well-defined notion of state that the system itself doesn't know, it just goes from these images to control actions, how do we predict safety in a calibrated way for these systems? That's another interest of mine. More on the intervention side, we're working on repairing controllers to ensure that they perform well in certain situations, and then we want them to perform well in yet other situations without breaking the first ones. So this is a kind of a high assurance alternative to retraining if you don't want to lose any of your guarantees, but you want to improve your controller further. And finally, I'm broadly interested in actual causality or Halpern-Per causality in CPS for diagnosis, for repair, for online monitoring. So if you're interested in that too, please reach out. And also, I encourage you to check out the recent papers, one in Conference on Assured Autonomy, one still in submission on these topics. All right, so enough about research. This is the last slide. To summarize, I told you about this verified and monitor methodology, which basically says, well, we build the system, now let's verify it. That gives us some guarantees, but they get broken, but we're going to fix it with the monitors. And what my recent work does, it says, well, do the monitors really fix it? And what does it take to get the monitors to fix these problems, which means imposing an upper bound on the calibration error of the monitors. And I told you about a couple of settings where we were able to impose this bound, and it seems to work in practice. That's it from me. Thank you for listening, and I'm open to any questions.
Great, thank you for the talk. It was very interesting, and indeed, I will be monitoring the chat. So if anyone wants to ask in the chat, I will read out the question. But please go ahead.
Yeah, if I may, Ivan, well, first of all, thank you for the very interesting talk. Definitely, I keep seeing a lot of work on this topic, and this is really a nice contribution. I'm going to ask you a big picture kind of question. So let's say that your monitor tells you that something is happening, okay? That your guarantees somehow are not going to be satisfied, right? So over the next 10 seconds, something will happen. How do you see this used in a system, right? So what do you do when if one of your alarms goes off?
Yeah, that's a good question. So there is several possibilities in practice. The most straightforward and immediately accessible one is to have the human sit there and hopefully the plan or the prediction horizon is long enough for the human to realize there is an alarm, look at the system, understand what's happening, and do something to it. But of course, we want more automation. So there is two ways in which I see this going. One is a tighter integration between monitoring and planning. And I've seen some work on that already. So let's say this predicted probability is another input to your planner, to your MPC controller. And that, well, tells the controller some information, or even a neural network trained to, to relax, slow down, and not push as hard when the monitor is telling us that something's going to happen. I mean, people do it a lot. You know, if you're entering the intersection, there's some guy running around waving his hands. You don't know what's happening, but you're probably going to slow down and keep observing rather than try to speed up through the intersection. The second way of dealing with it is kind of a separated meta-level hierarchical control that will not integrate closely with the nominal control loop, but it will have some high-level interventions or recoveries that will say, okay, in the case of the underwater vehicle, it will say, well, looks like we're going to get stuck in the weeds and we're losing sight of the pipe, so we're just going to surface. So it's a discrete action. Yes, you take it when things are getting bad, but you have, you know, good hopes for this action, and you don't put it in the nominal control loop.
Right.
So these are the options.
Mm-hmm. Yeah, but then essentially you're thinking of this, correct me if I'm wrong, okay, as something as in some kind of like a hierarchically nested controllers, right? So where you switch from one to the other when your monitor goes off, right? But then is a problem of interest there is the safety guarantees, not the monitoring, but of the overall nested system. Or another thing that you can say is, okay, so let's say that you are on this, you know, some autonomous system, right? And then you switch to human control. Wouldn't you need to be monitoring the human in a sense to make sure that you don't make a bad situation worse?
Absolutely, absolutely. I mean, this is all the interesting stuff in the human-machine teaming. You know, is the human competent enough to take over? Is the human paying attention to take over? Will the human actually perform better than our suite of controllers? So I think this is all great open questions. For the nested part, yes, the question is, what's the safety of the whole system when we switch? And, well, yes, I think it's an open question. It gets harder to answer that, because if you're switching away from your, you know, nominal best performing controller, then something has been broken, like, you know, your dynamics doesn't work the way you expect, and so you're in a tough position there to make safety guarantees. So I think we need some new insights to be able to pull that off, because the old tricks stop working when we're already in an exceptional situation that we don't know much about, and our models don't work, or our perception doesn't work. I mean,
but then in a sense, so I'm just thinking of the way that you presented was one of your first slides, you know, probably your first or second after the title, when you were talking about what does it mean to have trustworthy systems, right? So safety versus trustworthiness, or
yeah. You can go there. Like here.
Right. So in a sense, you could have the, I mean, I don't know how you want to call it. Let's say the one of the extreme, right? So you have a very safe controller that doesn't do much, right? And then you have a hierarchy of other controllers that you enable if you're confident enough that those controllers will work well, right? So will make you go faster without crashing. And then you think that, oh my goodness, maybe I'm gonna crash. So then revert, you know, to the safer controller or something like that, right? So where you are not giving up on safety, but you're possibly improving on some other measure, you know. Does it make sense?
Yeah, I think that's a reasonable vision. So kind of a substantial evolution of the simplex architecture with just two controllers, but now we have a whole array of them and we can pick them. I mean, the necessity for picking and having these separate contexts is mostly to deal with the human engineering complexity. Like we can't just take a giant neural network, an unbounded open world, and have any trust in what's going to happen. We can split it into contexts, we can bound it with assumptions, and then have a controller that performs well on ice, and so on and so forth. So yes, I think that's a plausible vision.
But
to
for
where this
me,
is
my
going.
point is that, just having an alarm that goes off, unless you think of it as something that is part of a bigger system, is not really telling me much.
Oh,
Right.
absolutely. I agree with you. I think
Yeah.
we need to be clear that this work is focusing on giving the alarms that have some meat behind them, that have some backing, and we cannot stop here. And I don't plan to stop here. I just, address the areas that seem to be missing some of these guarantees. But absolutely, we need to feed it further and create a hierarchy and of controllers, or the reasonable takeover or handover to the human, and so on. Yeah, I fully agree with you.
Yeah, thank you. And I don't want to take too much time. So
Yeah, no, thank you for attending, and thank you for the comments. I agree with you. All right, well, looks like
Yeah, I think then we
appetite is
finished
done.
perfectly on time as well. Thank you for the great talk. It was very interesting to hear on this topic. And
thank you for having me.
we'll follow up with the link, the recording, and everything once edited.
Absolutely. Thank you. And,
Great.
have a
Thank you
good
so
night.
much. Yeah, have a good day, you too. Thanks.
Bye.
Bye.